Hello and welcome. My name is Elhelw. Today I'm going to be talking about a topic and a question that I've been asked a lot, which is what is the difference between OLTP and OLAP systems? Which of them do I need for my application and so on? So let's dive in and see what those are and what are the differences between them. First of all, let me start with an introduction. Databases. We've been talking about databases all this time, and I think by now everyone knows that databases are used pretty much everywhere in our day-to-day life. Whether you are depositing some money into your bank account or transferring money from one account to another, or if you are shopping at a grocery store or online, there's a database involved in those cases. If you are ordering an Uber or a cab or something, there's still a database in that app that you're using to order the Uber. If you are generating some reports for your company for work, there's still some database involved which has all the data that you're using to generate that report. So pretty much in everything that you're doing, or most of the things that you're doing, there is some database involved, whether you directly know it and work with it, or it's just there in the background that you're not really dealing with it yourself. So when we talk about databases at a very high level, they can be classified into two different types. There is OLAP and OLTP. Some of you may have heard those terms, some of you may already know what they mean, but some people do not know, and that's why we're making this video. Those two kinds are used to describe two different kinds of databases. This classification implies the kind of functionality or the kind of features or the kind of operations that is required from each type of database, and they serve two different purposes, two different types of applications. As a result of that, those two types of databases are typically designed to be more efficient for the kind of operations that each of them is required to do. So if you are building an application and you're wondering what kind of database do I need for my application, you need to understand what your application is doing, which will tell you which category of those databases you should be using. So with that, let's discuss the two different types and understand what is meant by each of them. Starting with the first kind, which is OLTP. OLTP is an acronym. It stands for Online Transactional Processing. The focus here is on transactional. And just as a side note, transactional doesn't really necessarily mean the kind of database transactions that we've discussed in a previous video, but it means any transactional work, basically any kind of operational day-to-day work that happens. For example, again, this could be in banking, in shopping, when you're doing some transaction to check out your cart, pay for your the stuff that you bought, or if you have like a warehouse that you're managing the inventory in that warehouse, you're trying to figure out what items came in, what items came out of the warehouse. So all these different little transactions that are happening in your day-to-day work. This could also be in social media, when you're reading comments, when you're posting stuff on social media. All these day-to-day operations are considered transactional processing. Other examples include things like hotel reservations, ticket sales, all those things. Any stuff like day-to-day things that you do that usually involves a very limited amount of data is considered transactional processing. For an OLTP system, typically we have the database in the back end, and we have many users accessing and working with this database concurrently. Usually the number of users accessing are huge. Again, think about a bank website. There's like so many customers or clients working with that bank website. If you're thinking about something like Amazon or any e-commerce website, there are so many users accessing and working with it concurrently at the same time. So this is a feature of OLTP systems in general. Each of those users usually interacts with the database by sending some request, and then the database will process this request and send back the result of that request. These requests are typically very short and simple, and they could be either writes or reads. So, for example, in the banking context, you could be sending a request to check your account balance. This is a read request. Or you could be sending a request to deposit money in your account, which is a write request because you're updating the account balance. In the context of social media, reading a comment is a read request. Posting a comment or liking a post or anything like that is a write request. Again, you're making a change. In the context of shopping, searching for a product, that's a read request. checking out your cart, that's a write or update request. So again, all of these requests happen to be very short, very simple, maybe have like one filter or something, send me all the products that have this criteria, or give me the account balance of account number so and so and so, or update this account, add value of 100. So usually they're very straight, very direct requests, doesn't involve a lot of processing, and usually the result returned is fairly simple and limited amount of data. So this is kind of what happens in online transactional processing systems. So again, to summarize that, to give you everything that we've talked about so far. So OLTP systems, they deal with current operational data. They handle the day-to-day operations of a business. It has many concurrent users. Usually those users are either customers or employees. For example, if you're at a grocery store, the employee at the cashier is handling or dealing with some kind of database. This is usually an OLTP database. The requests are fairly short and simple. They involve both reads and writes, and they require fast response time. Again, when you're dealing with an OLTP system, you're doing all these requests all the time. You don't need to, or you don't expect to wait 5 minutes until the response comes back to you. You expect the response to be instantaneous. So it requires this very fast response time. On the other hand, for OLAP systems, so OLAP is also an acronym. It stands for Online Analytical Processing. So the emphasis here is on analytical. So to contrast that with what we talked about in OLTP systems, here we're not just doing the day-to-day work. Here we're trying to do some analysis on the data, and usually we're using historical data and aggregated data. So for example, again, if we're talking about a company's data, the day-to-day work will just work on what we have today. Like in a warehouse, for example, this is the stuff that we have today in the warehouse. This is what's going, what's coming, and so on, all the current data. But for analytics, you may want to see, okay, what did I have 2 years ago, 3 years ago, 10 years ago? So you need all that historical data so that you can use it to do some analysis, maybe to do some predictions for future things that you want to add to the warehouse and so on. So you need that historical data. Usually the amount of data that you're dealing with in OLAP systems is huge. It can also include some aggregated data. So you might do some pre-aggregations if you know that you always want to look at some particular averages or sums and stuff like that. You can also pre-compute those aggregates and store them as well. The database part of an OLAP system is usually referred to as a data warehouse. Again, this is one term that you may have heard about before. The data warehouse is where all this historical data is stored, and this is where the OLAP operations or the analytical operations run on that data. And like I said, the use case here is to make some analytics, generate reports, identify trends, do some forecasting, generally support the decision-making process of an organization. So what does the interaction with an OLAP system look like? Here we usually have a limited number of users, not as many as for OLTP systems. And it's usually either analysts, data scientists, for example, or also automated BI or business intelligence tools. So those are usually the users of a data warehouse or an OLAP system to come up with those analytics and generate those charts and reports and so on. In many literature or in some other videos, you might see that the data warehouse is usually represented as a cube. Of course, there are many ways to draw a cube. I just chose this because it looked cool. But the reason this is used is because it indicates the dimensionality of the data. The data is highly multidimensional. And by multidimensional, I mean it has many things that you can filter on or group by or aggregate on. So these dimensions could be things like regions, users, customers, product categories, age, date. So all are different dimensions that you can filter by. You can say I want to analyze the data between this date and this date. So I'm filtering on the date dimension. And I also want to group by the product category, and I want to group by the region. So I'm grouping by those different dimensions. And then I want to sum, the amount of sales. So this is what I mean by the dimensions of the data that you can use to filter or to group by. Of course, a cube has only 3 dimensions, but it's just a representation. In reality, the data can have as many dimensions as you want. So again, to recap OLAP systems so far, so we said that we deal with historical and aggregated data. The purpose is to produce these analytics to identify trends, have some insights in the data, maybe forecast things in the future based on historical data and whatnot. The users of these systems are analysts, data scientists, BI tools. The queries are usually complex. We didn't talk about this part, but they include lots of joins, aggregations, grouping, filtering. They can also include things like analytical functions, things like time series analysis, for example, and whatnot. So the queries are much, much, much more complex than what we have talked about in the OLTP case. As a result of that, they usually take longer to answer, but that's okay in this case because these are not part of the day-to-day operation. Usually when you're running an analytical query, you're trying to generate a report, you expect it to take some time, so that's okay. And the last thing is that these operations are usually just read-only. We're not making any changes to the data. We're just reading the data and analyzing it and looking at it from different angles and doing different filtering and different aggregation and so on, but it's all read-only operations. Okay, so after we've seen what are the purposes of OLTP and OLAP systems, let's look at some of the differences in terms of schema design and also in terms of the features supported by each of those systems. So let's start with schema design. Again, when you're designing the schema, this is part of the designing your database. It should reflect the application and what you're trying to do, and make it easier for you to do the things that you want to do. So let's recap again for OLTP. What we're trying to do is that we're trying to execute requests, both read and write requests, that are very simple, very short, usually require very fast response time, and we want to support a large number of concurrent users. And also we want to guarantee that the updates that are happening concurrently still yield consistent data. So how do we organize the data in a way that accomplish this? For OLTP databases, usually we use a normalized schema design. We've talked about normalization in a previous video. I will put the link in the description as well as up on the screen. So please take a look at that if you haven't seen it so far, because it explains a lot of the things that I will go over now, but very quickly. So normalized schema design means that we try to eliminate or reduce redundancy in the data as much as possible. So we don't want repetition in the data. We don't want the same, let's say the same ID and the same customer to be repeated multiple places. We want the data to be just stored once, and then we may have different references to it. That's why we have this way of designing the data. We can split it into multiple tables and use foreign keys and so on to reference other tables. This eliminates things like the insertion, deletion, and update anomalies. Again, refer to the normalization video for more details on that. Basically, this helps us in maintaining data in consistent state. It eliminates the potential problems that may happen when we have redundancy. If you end up, let's say, updating one copy of the data but forgetting to update the other, or there is a bug that ends up in that result, which you may end up with inconsistent data in that case. So if you eliminate that redundancy, you eliminate the chance of that happening, and you increase your likelihood of having consistent data. So most OLTP systems tend to have, or if you're designing an OLTP database, you tend to use that normalized schema design. Of course, there are exceptions to that case when you're dealing with maybe non-relational databases, something like MongoDB, for example. It's still an OLTP database, but it's not relational, so it uses a denormalized system, which is a document database. But if we're talking about relational databases, usually we go with a normalized schema design. In addition to helping us with the consistency of the data, it also helps with the speed of the updates and the reads as well. You might actually disagree, or you might say, okay, well, when we talked about normalization, we said that normalization, because it splits the data across multiple tables, this ends up resulting in slower queries, because then you have to do all these joins and so on. Generally, it's true, but when we're talking about OLTP operations specifically, most of the queries are simple enough that you don't need to do many joins. Usually, maybe you need to join maybe 2 tables, but most queries either don't have a join or just have 1 join. So in that case, you don't deal with that slowness that's coming from joins. You're just accessing 1 table to read or write to. So then it becomes super fast, especially that we don't have that repetition or redundancy. Then you need to update only 1 piece of data rather than 100 or 1,000 if the data is repeated. So again, this makes the updates a lot faster than a denormalized approach. Now for OLAP, what does the schema design look like, right? So here we have different requirements. Here we're looking for supporting queries that are much larger, much more complex, that deal with a lot more data. It's only read requests. We're not looking to support write queries or write requests. We're looking to support complex operations like joins, grouping, aggregation, analytical functions, and so on. We're not really concerned about high level of concurrency because we don't have that many users accessing the data. So we don't really need to worry about consistency or anything like that, because also we don't have updates anyway. So that's not a concern. So in this case, a normalized design doesn't make a lot of sense because it doesn't really serve the purposes that we're looking for. What we typically do in an OLAP database is we use something called the star schema. Star schema is a denormalized design that has something called a fact table, which is usually huge. It's like the center of the star schema. And then we have these dimension tables that are linked, from the fact table by foreign keys. So because it looks like a star, you have, one table in the center, and then you have all these dimensions coming out of it. That's why it's called a star schema. The fact table has a lot of repetition in it. That's why it's denormalized, because it has references to all these dimension tables. So the same combination of, let's say, of customer and store and region and product category may be repeated a lot of times in that fact table. If we were to have updates, that would have been a problem. But because we don't have updates and we only have read-only operations, then that's okay. This makes it easier for us to read that data from the fact table and filter by different things or aggregate by different things, because it's basically makes it unnecessary to do many joins, because we have all the data, or most of the data at least, that we care about in that fact table. We only need to go to the dimensions when we need to get some extra information about some of the dimensions. For example, if we have the customer dimension and we want to get like the customer address or something, then we might need to go to the dimension table. But in most queries, we may not even need to do that. There is an advanced version of the star schema called the Snowflake schema, not to be confused with Snowflake, the database engine. It was named based on that, actually. The Snowflake schema is kind of like a star schema, but each of the dimensions will have its own dimension, so it becomes like a snowflake. You have, central table and then multiple dimensions, and each dimension coming out of it more dimensions. So that's why it's called a snowflake schema, but I'm not going to get into the details of that in this video. Just know that this is another way of representing the data. Like I said earlier, another thing we can do is that we can also store pre-aggregated values. If we know that certain queries always requires certain aggregations, we can pre-compute those and store them as part of the schema that we have, which is basically like materialized views. So this can be stored as materialized views or in different ways. Okay, so now that we've explained the schema design of both OLTP and OLAP systems, how do these interact, or do they interact, right? We talked about the OLTP database having only current operational data, and the data warehouse or OLAP databases having historical data. Well, in many cases, the current operational data that we have today, at some point it becomes historical data, right? And we should incorporate that into the data warehouse to be able to do whatever analysis that we want. So there is some usual interaction between the two. Let's see what that looks like. So given the two kinds of databases that we talked about, again, for OLTP databases, we know that there's so many users using it, issuing these requests, having these transactions with the OLTP database. At some point, periodically, we run a pipeline called ETL, which stands for extract, transform, and load. These three operations happen to take data from the OLTP database into the data warehouse or the OLAP database. Again, you may have heard about the ETL term before. It stands for three different operations, not a single operation, because you extract the data from the OLTP database, you transform it into a different form, and then you load that result into the data warehouse. Like we said, the schema is different, so you may have an OLTP schema that looks like this, again with a normalized schema with all the foreign keys. You extract the data from that using some query, then you transform it into a different form, different structure, and you load it into the tables in the data warehouse that has a star schema into it. So this is what ETL means. Again, I'm not getting into any more detail than that. If you would like more information about ETL, please let me know, and I will try to get to that or answer that separately. So now we have all the data that we need in the data warehouse. Again, that ETL pipeline It runs, periodically, every month, every year, whatever it is. And then you get all that historical data that keeps getting, accumulated in the data warehouse. And then you can run the analytics or the queries that we have to generate, all these charts and reports and so on the data warehouse. So far, we've talked about the schema design. We've talked about the difference in terms of requirements from both systems. The one thing that we haven't talked about yet are what features do each of these systems support. So of course, each system, whether it's OLTP or OLAP, needs to support some features that will achieve the requirements that we have. So again, for OLTP, I'm going to repeat this part because it's important. The requirements are that we have all these short queries, both read and write queries. We care a lot about concurrency. We care about consistency. We care about transaction processing in general. So what features does a database management system support to be able to achieve those? So for OLTP-focused database systems, the first thing that comes to mind is obviously asset compliance. Again, we talked about asset properties in a previous video. This basically stands for atomicity, consistency, isolation, and durability. So any OLTP system must provide asset guarantees. Second thing is real-time performance. Again, we talked about the response time for OLTP databases because you need to have this instantaneous response. So it needs to have this performance that is super fast, that can process all the requests and return the result in almost real time. It needs to support high concurrency, be able to deal with so many different requests coming at the same time, because again, we have so many users. Imagine if you have something like Amazon or a banking website, how many users are accessing that at the same time. So it needs to support that high concurrency. Many of those users would also be doing updates, so it needs to be able to handle all those concurrent updates. So to support that, it needs to handle things like sharding or replication, which are features of distributed databases in general. And finally, some examples of database systems that support these features are MySQL, Postgres, Oracle, MongoDB as well. So all of these databases are, some of the very common examples of OLTP databases. For OLAP systems, the requirements are that we have these complex queries that have joins, aggregation, grouping, and so on. The queries are fairly large. The data is huge. We don't really care about concurrency as much. We don't really care about consistency or asset properties because we don't have updates anyway. So what features do we need to support that? For OLAP systems, we need to be able to manage large data sets efficiently. Again, because we have all this historical data that we need to deal with. So we need things like partitioning or columnar storage and so on to be able to handle these huge data sets. The system needs to support complex and multidimensional queries, again, because this is the kind of queries that usually runs in OLAP databases. And to be able to support that, it needs to have a powerful query optimizer. We have talked about the query optimizer in the past, and we know that when you have a large query, this means that you have many different possible execution plans. So the optimizer needs to be able to enumerate all these different plans and then choose among them using its cost model. So you need a really powerful optimizer to handle this kind of queries. When you have simple queries in like an OLTP, the optimizer may be not as needed. And specifically, you need to have optimizations for aggregations and analytical functions and so on. So these are the heavy features of analytical queries. Some of the most common databases that handle this are Snowflake, BigQuery, and Amazon Redshift. And of course, there are others. There are also some database systems that handle both OLTP and OLAP requirements. Oracle is one of those. SQL Server is another one. There are many others. Most of the big established database management systems usually handle both kinds of operations. So if you have one of those systems, you may be able to satisfy both requirements with that. But I think most, especially large organizations, tend to have separate systems for the data warehouse versus their OLTP database. Now, why is it important to pick the right system for your application? Like if you're building an application and you need a database backend, why does it matter? Why do you need to know OLTP versus OLAP? Because as we listed, we have seen that each of them supports different functionality, right? So if you pick the wrong one, then your application either will not work very well, maybe will not be very efficient. Maybe some functionality that you need will not be supported. So for example, if your application is doing OLTP kind of work and you use an OLAP database or a data warehouse database that's optimized to be a data warehouse, then it may not be very efficient in terms of fast reads and writes. It may not have good asset property compliance, may not support all of the asset properties. It may not have good concurrency support. So then when you plug that into your application will be slow. It may not have the guarantees that you're looking for. It basically will be in trouble. The same thing in the opposite situation. Like if your application is doing more analytical work, OLAP kind of queries, and you choose a database that is optimized for OLTP work, then it may not support complex queries. It may not be able to work with huge amounts of data. It may run out of memory. It may be very slow. It may be doing a lot of overhead to enforce the asset properties, which you do not need in this case. So choosing the wrong kind of system is a problem for your application. This is basically the first step when you're designing an application, to know which database do you need based on what the requirements of the applications are. So with that, let's summarize again what we talked about today. Today we compared OLTP and OLAP systems. OLTP systems are transactional or operational. They handle the day-to-day work. They usually work on the current data, data that is operational. It's just like, the things that are going in and out of a warehouse, for example, or what is the current state of a bank account and so on. The end users are customers or employees. Usually there are so many concurrent users using the system at any given time. Data access is both read and write operations, usually very simple reads and writes, not very complicated in terms of the queries that are posed to the system. And the data or the schema design is usually normalized to help achieve the requirements that we have here. On the OLAP side, we use those for analytical queries and decision making. The data is usually historical data from 10, 20 years ago, because you need as much data as you can get to make those decisions, to make predictions based on history and so on. The users of these systems are usually analysts or BI tools as well. Those queries are usually read-only. You don't make any changes to the data once the data has been imported using ETL from your OLTP database. You don't do any further updates. You just view the data from different perspectives with different aggregations and so on. So all the requests are read-only. Those requests are usually very complex with joins, aggregations, analytical functions, and so on. And the best way to represent the data is using the denormalized schema, like star schema or snowflake schema, and so on. I hope this video clarified the difference between OLTP and OLAP. If you still have any questions or any things that are not super clear, please let me know in the comments and I will try to answer those as fast as possible. If you like the video, please hit the like button. If you have not subscribed yet to the channel, please do so. That will help me a lot. And with that, thank you so much for watching, and I will see you in the next video.